So, in our previous class we have seen the bandwidth of FM modulated waveform, and we have this alternate representation of the FM, right. In order to derive bandwidth, we first evaluated this alternate form, and then using this we proved that the FM modulated waveform has a infinite bandwidth. So, next we will define what is narrow band FM and how to generate a narrow band FM signal. So, this was our alternate representation, AC cos 2 pi FCT minus CF AT sin of 2 pi FCT minus CF square 2 factorial A square T cos of 2 pi FCT plus S. So, if we make an assumption, narrow band FM, if we make assumption that magnitude of CF80, the maximum value also for all, I mean the maximum value of this quantity is very less than 1, then we can neglect the higher order terms. I mean by higher order means second, third, fourth and other higher order terms, and our FM signal would become cos of 2 pi FCT. So, by making this assumption we yield, I mean this assumption yields CF AT sin of 2 pi FCT. So, this is our narrow band FM signal, and this is a narrow band assumption. If we see the amplitude, the envelope of this signal, this is AC cos square 2 pi FCT plus CF square AT square sin square 2 pi FCT. Excuse me. What is the envelope of this? A cos 2 pi FCT plus B sin 2 pi FCT under root A square plus B square, right? Magnitude, correct? This might be a function of T. So, in our case, if we use this formula here, the envelope is, or the magnitude is AC 1 plus CF square A square T. So, and now we know that CF AT is very less than 1. So, we can, this quantity will be very less than 1, right, this whole quantity. So, you can approximately say that it is a constant envelope, but there is a slight variation you can see, I mean there is a very slight variation in amplitude. So, what we have seen, what is a narrow band assumption, and by using narrow band assumption we can get a linear form of FM signal. Why I am calling it a linear? Because if you remember our DSBSC signal or our amplitude modulated signal, what is the typical structure of an amplitude modulated signal? This, right? So, if you compare, this is quite similar, right? So, by using narrow band assumption, our narrow band FM signal is AC cos 2 pi FCT minus C of AT sin 2 pi FCT, and it is similar to the expression of AM wave, and we have also seen that there is a slight, see, if you have a perfect FM, if you remember, yeah, if there are infinite terms, okay, or you can go here only, yeah, before approximation, this FM has a perfect constant amplitude, constant envelope, right, but due to approximation you see that there is a slight variation in amplitude, right. So, because of the approximation, our narrowband signal has some amplitude variation. And in order to tackle this problem, we use the device that is called band pass limiter. We will study it later, but first you see what are the two observations when we see our narrow band FM. We have a FM signal, right. This is the alternate representation of FM signal that we had derived in our previous class. By using this narrow band assumption, we get a linear form of frequency modulated waveform or narrow band frequency FM. This narrow band FM is linear, but the envelope is, there is a slight variation with time, right, and we say that we can tackle this with using band pass limiter. Okay. So, let us first study generation of FM signal, FM narrow band FM. So, what is the expression for narrow band FM? AC cos 2 pi FCT minus CF AT sin 2 pi FCT. So, in order to generate this signal, what we have to do? We have to use this is your AT, you have to multiply it with sine signal, sine 2 pi FCT. So, if you remember your DSB-SC modulator, DSB-SC modulator is nothing but a product modulator where we multiply your input waveform with the carrier. Here carrier is sine. So, first we generate a local using a local oscillator a cosine wave, and then we use a minus pi by 2 phase shifter which will generate a sinusoidal signal minus AC sin 2 pi FCT, sorry, plus pi by 2. We will use a plus pi by 2 shifter, so that you get a minus A sin 2 pi FCT, and when you pass it through DSB modulator, it will multiply it and also provide some gain in form of CF, you can set it, right, MT sin AT sin 2 pi FCT, and then you add it with the carrier and you get a narrow band FM. So, this is a block diagram of a narrow band FM, block diagram in order to generate the narrow band FM waveform. So, just remember this. Okay? So, in order to generate a phase modulated waveform, what you have to do? You have to just replace CF with KF and your AT with MT, right? This thing you remember. This AT is nothing but integral of MT, right? From our previous discussion, you know that AT is minus infinity to T mu d. So, if your message signal is given to you and your carrier signal is given to you, how can you generate your narrowband FM signal? By this, you have to first integrate, you get AT and you this. And in order to generate PM, you have to just use MT, right? And you have to replace CF with KF. Great. And yeah, so in our, I just told you that slight variation in amplitude or amplitude variation of FM signal waveform can be eliminated by using band pass limiter. Correct? So let's study or discuss the functioning of the band pass limiter. Band pass limiter is a hard limiter, consists of hard limiter followed by a band pass filter. Okay. And hard limiter, what is hard limiter? So just to first write this is hard limiter followed by band pass filter. And if you pass any FM signal of this type, then the output of this is this 4 by pi cos of omega ct plus theta t. It means the variation in amplitude is mitigated and it is constant now, right? And the hard limiter, the input output characteristic of hard limiter is this. When input of the hard limiter is a negative signal, it will give you -1, and when input to the hard limiter is a positive signal, the value of the signal which we fed to a hard limiter is positive, the hard limiter will provide you 1. So let's verify this. Our claim is if we pass any signal of this form to the, this is together consist of band pass limiter. Band pass limiter. Functioning of band pass limiter. So first study, first let's focus on hard limiter block, right? So if we pass a signal of this type, a sinusoidal signal, then if this is input, right? If this is the input, right? With time, right? So how the output of the hard limiter will look like? For the positive values of input, the output will be 1, for the negative value it will be -1. So it will be a square wave, right? It will be a square wave with, the height will be 1 and -1. And what will be the values of those, these points? The zero crossing will be preserved, right? The zero crossing or the frequency content of this signal will be preserved, but the variation, the amplitude now is either +1 and -1. So this is the output of your hard limiter. So how can you write output? If this is your hard limiter and this is the output, and input is ACT cos of omega ct plus theta t, right, plus 1 if this whole value, this value is greater than, we just replace it with theta tilde t, cos of theta dash t is greater than 0, minus 1 if cos of theta dash t is less than 0. And pictorially the output will be a square wave of height 1 and minus 1, as you can see in this figure. So, any angle modulated waveform, what was the aim of our band pass limiter? To avoid, to mitigate the slight variation in amplitude of any FM signal, right, because in FM signal the envelope or the amplitude must be constant. Okay. So, if we provide here the input is FM signal, okay. In our case it is a particular NBFM signal, you can say, or it can be any FM signal. Any FM signal which have slight variation over amplitude, if passed through BPL or band pass limiter, will give you a constant amplitude signal, but the information which is embedded in phase or in angle will not get disturbed, it will be preserved. So, as we have seen, if you provide an angle modulated signal to hard limiter, the output will be first square wave, and then we pass this square wave through band pass filter. Why do we pass this square wave through band pass filter? In order to see that, we first represent this square wave in alternate form given by Fourier series. If you remember, any periodic square wave with period 2 pi can be written in Fourier series as you know this from your signal and system course, or you can just also derive it, that any square wave is given to you with period 2 pi, and what should be this Fourier series representation or expansion, Fourier series expansion. Okay, this is Fourier series expansion of periodic square wave with period 2 pi. Okay, so as I told you that the aim to do this expansion is to see why do we need band pass filter. At the output of the hard limiter, we have seen that any angle modulated signal will have a periodic square wave, right? A square wave, you can say, not I mean, it might not be having a period 2 pi, it depends, right? It depends on your modulated signal. The only point which you have to focus, that the zero crossing will be preserved. Whenever your FM modulated signal will cross these zero crossings, the square wave accordingly will behave, right? So, as you can see from here, this is your square wave, right? And okay, yes. So, this is your hard limiter, and if you provide a cos theta dash, as I told you here, right? Sorry, this ACT cos theta dash t. BCT cos theta dash t, ठीक है. So since we are using theta dash, you can also replace it with theta dash. The output will be a square wave of, and which you can write like this, and the alternate or the Fourier series expansion will be this, but theta dash for any FM signal is this, right? For FM signal, you know this, 2 pi kf mu du, correct? So you have to put, when you put this value of theta dash here, what you will see that this will be, this term will have a, will be around the spectrum of this signal would be centered around Fc. The spectrum of this will be centered around 3 Fc. The spectrum of this will be centered around 5 Fc. So if we use a band pass filter which is centered around Fc, all those terms will vanish and only we will have this term at the output of the band pass filter. So once we pass this signal from the band pass filter, the output we will get is, just write it, V1 theta dash, the output will be 4 by pi cos of theta dash, correct? Or you can also write t here. So this is your, so you can see that if we pass any signal of this type from the band pass limiter, the output is, this is your V0 theta dash, this is your V1 theta dash, right? So V1 theta dash is 4 by pi cos theta dash. You can also write it t, it's not a big. So you have to replace theta dash with theta t, theta dash t everywhere. So the slight variations in amplitude or the variation in amplitude can be mitigated by using the band pass limiter. So if we summarize our discussion today, what we have seen, what is a narrow band assumption? By using narrow band assumption, we can approximate our frequency modulated signal, this is your frequency modulated signal, to a narrow band frequency modulated signal, and if you see the, because of this approximation, the amplitude will be, the variation, there will be some slight, variation in amplitude of this signal, okay. And then we have seen the generation of FM waves, and we have seen how to mitigate or how to remove this variation in amplitude. Thank you.